Good evening, everyone. Welcome back to NPTEL live session for week 7. We'll be shortly starting the session after waiting for 3-4 minutes for rest of the people to join. Okay, so we can start the live session now. So we are going to discuss about the concepts that have been learned in week 7 lectures given by Professor Arnab Dutta. So before starting with the week 7, if there is any doubt from the previous sessions, any question related to the assignment or something, that you can speak up now, or in the end of the session you can let me know if there is any query. So today we will be, these are the assignment problems that I have taken for the week 7. There are only 5 in number, but each and every question would be covering whatever has been taken in the week 7 thing. So here are the topics that have to be covered in during this session. Firstly, the applications of circular dichroism. Some of them we have already seen in the last session. We have understood the concept of circular dichroism, different various spectra with which we can identify different structures. Now, underneath of this circular dichroism, we have two important things to talk about: induced charge transfer bands and chirality in the charge transfer bands, and G-complex formation and topology. Second, we will be talking about, since we have to shift from the circular dichroism, now we'll be touching up the MOSFET spectroscopy, which is the second half of this course. So before starting that MOSFET spectroscopy, to understand the spectroscopy terminology, we'll be talking about a little description about the NMR, EPR, IR, UV, all the other spectroscopies which are on a daily basis we use in our research labs and for the characterization purpose. So let's start with the applications of the circular dichroism. since it's a week, we have not met, so there could be a possibility that circular dichroism, again, you guys have skipped it or you do not remember it. So I'll just give you a brief of it. Since we talked about the LCP and RCP, which are the left hand circularly polarized light and right circularly polarized light. So because of that, we got to know that they are having helical motion, and due to the change in absorbance in presence of a chiral material, that leads to show circular dichroism. That means two kinds of absorbances would be happening. Now, related to that, we went ahead and we saw that how we see the chirality in biological systems. So we talked about the amino acids, and then we saw they are chiral in nature except the glycine. And among the amino acids, why do we talk about the amino acids? Because our basic structure of our biological system, DNA, RNA, they comprise of the peptide bonds and these units, amino acids, proteins, etc. So that's why we wanted to understand how we can use the CD spectroscopy to get to know about the structures of the DNA, RNA, different forms they can have, and their unit is protein. So among proteins also, we classified them into their primary or first degree structure, where we saw that there would be a chain of all the amino acids. There would be a sequence of amino acids, but they would be in a linear fashion. Then we went ahead and saw secondary, which comprises of alpha helix structure, beta sheet, random coil. So alpha helix, we know that C terminal, N terminal would be having a dipole moment interactions. Beta sheet would be two sheets where, because of the hydrogen bonding, they were forming that secondary structure. And random coil is having no structure. The unit C terminal, N terminal could be from any side, but they are not having a specific structure. And the third category we saw was tertiary. Tertiary was having a combination of both alpha helix and beta sheet, and quaternary was actually having a combination of these tertiary proteins. That means instead of having one tertiary protein, there would be like 4 globules. So it would be one tertiary protein, second tertiary protein, third tertiary protein, fourth tertiary protein, as we saw in case of hemoglobin. So up to this we discussed last time, and also we identify what would be the structure, how alpha helix, beta sheet, and random coil is going to be seen in the your CD spectroscopy. So this is positive and negative. And in alpha helix, it starts from positive. It will show two negative bands in the negative side. There are the values 190 nanometer, 220, 202 and 218. Whereas in beta case, it starts from 195 and will be having a 213 or 18 something. And random coil is having a signature starting from 195 but in the negative region and going to this side where positive is there. So these three, this is alpha, this is beta, and this one is random coil. Your x-axis is lambda in nanometer. So this way we identify how we can distinguish alpha helix, beta sheet, and random coil. That means the different forms of secondary structure. Also, in this week, we saw that there is a point, there is a temperature called melting temperature. At this temperature, denaturation, or we can say change of one secondary structure to other, most probably alpha or beta will be changing to random coil. So this TM would tell you that certain temperature would be there at which the change will start. So that is the melting temperature. And if a system, if a protein is having high melting temperature, it symbolizes that it will require more temperature, more heating to convert from one structure to other structure. If some solvent, if you can take up the example of solvent. So say for example, if I'm taking methanol, so methanol is having a state of liquid at room temperature, but if I'll boil it at its boiling point, it will get vaporized. So it goes from one state of matter to other state of matter, depending upon at what temperature it is going, that it's called as boiling point temperature of the methanol. Similarly, in case of the proteins, there occur three different types of secondary structures. So depending upon the temperature that we are giving, it will change its form, but the temperature has to be high or low. Depending on that, we assume the situation that okay, the protein is having this stable structure because it is having high melting point, high melting temperature to change its one form to the other form. Hope this is clear. So now we will start our today's session, which is talking about the applications. So in application, we are taking first example. Say we have a complex, the cobalt complex, with certain amino acid containing ligands. So consider this cobalt, and here we have nitrogen bound. Here it is sulfur bound. Say for example, the cysteine or something. Here nitrogen, here sulfur. And this wavy nature is representing that this nitrogen is the amine, could be amine from the amino acid, and R could be anything. So that's why the wavy nature has been given. Here also, this is cysteine, and there could be any R group over there. So they are coordinating through sulfur and nitrogen. Now this is in +2 oxidation states. In presence of oxygen, firstly, one of the sulfurs got oxidized, forming S double bond O, and amino acid is still intact. And second time, in presence of oxygen, it turns to from cobalt 2 to cobalt 3, having the same structure, and in presence of some other ligands, maybe the solvent molecule also. So through series spectroscopy, we got to see the induced chirality in charge transfer bands. Say for example, here if we see, there's a change of oxidation state, and because of this S double bond O and having an amine group, because our amino acids are chiral, they induces the chirality into the cobalt system, and therefore the presence of the charge transfer bands, which happens because of the ligand to metal charge transfer or metal to ligand charge transfer or DD transition, So that enhances, or that will give you a certain kind of change in the peaks, which you will not be able to see in a normal optical spectroscopy if you just record and observe it. So CD spectroscopy helps you to identify, okay, the charge transfer bands are shifting or they are having more intensity. That is because of the induced chirality. Chirality is coming from the amino acids that are being attached. Even though the structure says that amino acids, these wavy nature, are nothing but the amino acid group, which is chiral, and that is not directly intact with your cobalt. If it had been, if it would have been directly, then there would be a different terminology. But it is coming from a group which is attached. Like we can call it as an indirect bond, indirect interaction. That's why this is called as induced chirality in charge transfer bands. So we can see the variation from cobalt 2 to +3, and also the significant variation in charge transfer bands, which would be, suppose the spectra would be coming like this way. So this region would be DD transition thing, because cobalt belongs to a 3D transition metal. So it would be having D to D transition over there. And this with the high energy and low wavelength, that would be a charge transfer. So we will see an increase or shifting of the band because of the induced chirality, and that has affect the charge transfer bands. Now, the second example that we have, that is the application through the CD spectroscopy. How do we get to know like bands are shifting or something like that? This is a case of optical spectra, whereas in case of CD spectroscopy, if this is coming like this particular way, something like that, maybe after the induced chirality, it is shifting or it is giving a different signal. So there would be a distinction using the CD spectroscopy. Similarly, taking another example of cobalt complex. So this complex is already there. So these are bidentate ligands, and here we are having nitrogen, which could be connected to this acid bond. Carboxylic acid would be there. So any amine, if you will see, they would be having COOH, NH2, R group, and H group. So these are connected to each other. So the chiral center would be having, that's why the wavy nature has been formed. So some CH2 or C molecule would be there and carboxylate present over there. Now it says that this complex acts as a catalyst for H2 production only in pH less than equals to 3. So this is a complex, and catalyst means that when we are adding some complex, that should increase the rate of reaction without getting involved in the reaction. Say, for example, if I'm adding the complex, so it should not participate in the reaction. It should just do a modification. It should reduce the activation barrier, but it should not get consumed. If I'm starting with A amount of catalyst, it should be regenerating. And at the end of the reaction also, I should be getting the A amount of this particular catalyst. If it is getting consumed, that means it is not at all a catalyst. That is called as the stoichiometric ratio. So whereas, so in research, in chemistry field, we have seen a lot of complexes doing a lot of applications, and that have been known as a catalyst system. And H2 production is a very important and burning area right now. So we need a source of energy. Also, H2 production is being seen as a source of energy. So we need to synthesize some complexes which can be acting as catalyst for this particular system. So the point over here is, okay, we said that it is acting as a catalyst, but why at a particular pH? Firstly, we'll understand why we have mentioned the pH less than equals to 3, and also how CD spectroscopy is helping in identifying this catalyst is working at this particular pH. So we will understand over here that at pH greater than 4 or something, that carboxylic acid stays as carboxylate. If you have pH less than equals to 3, there would be more H positive source. And even if you have this particular carboxylate, it can attack on the H positive and it can reform your COOH, right? But if we are giving pH greater than 4, that's a pKa value of the carboxylate to exist. So this will remain as C double bond O negative, and this O negative tries to bind with your metal center. So as I was showing over here, when this particular moiety will try to combine over here, there won't be any H2 production, because for H2 production, how the mechanism goes, for the H2 production, there should be something, if there is a metal and coordinating to that, there is a ligand, which is having an H source acting as a H positive, and there should be a possibility of having hydride. Metal hydride bond should be forming, and ultimately these H positive and H negative combine together to give you H2 evolution. I hope this is clear. If not, then please let me know so that I can explain more properly. Okay, so that is where we are emphasizing. If we need an H2 production, it has to form a hydride and it should have a H positive source. Okay, that is clear. After that, when we have, I said ki if I have a source of O negative that is in the ligand only, and it is blocking the position where H can come and attach on the cobalt from the both sides. So it is not letting the hydrogen to come and attach with the cobalt, and therefore there won't be any H2 production. Whereas in case of, if there is pH less than equals to 3, there would be a source H positive, and therefore carboxylate will be existing as a carboxylic acid only. There won't be a direct involvement of the carboxylate to the metal. Instead, if there is C double bond O, there is oxygen or something, C double bond O, OH, this H is acting as an H positive, and the H negative can come because we are giving a source where hydride can be formed, and they both combine together to give you the H2. So only at pH less than equals to 3, you can see the H2 production, but not other cases. This was the mechanism or the concept behind it. But how does the CD spectra helps in this particular case? So it was found that when at different pH, for example, pH 4, pH 5, pH 6 or something like that, when we saw the spectra, it was not giving, or if you will record a CV for that matter, cyclic voltammetry, from the electrochemistry part. So from the CD spectra, we actually saw that the nature or the distinct peaks were seen when pH has been reduced from pH 4 to 6 to pH 3. Only the peaks were being shifted, or new peaks were they started emerging at pH 3 or less than that. In region of pH 4 to 6, there was no change, not much change in the CD spectra. So the CD spectroscopy helps in detecting the pH of that particular reaction so that we can have more production of the H2. Also, using another technique, cyclic voltammetry, we found that at pH 3, it was giving a catalytic current. I do not want you to get confused with another terminology. So we'll skip this electrochemistry part for last session, that extra session where I'll be talking about the character table. So I'll be taking this electrochemistry part there also. So we'll be sticking to the application part of the CD spectroscopy. First, we saw that to find out that oxidation state of the metal has been changed from +2 to +3, and any chirality is involved or not. So that we got to know from the CD spectroscopy, because in normal optical spectroscopy, the absorbance level was changing little bit, but not distinctive peaks were coming. We cannot assure that, okay, this band is coming from this particular thing. We cannot give or precisely tell about the reason. But using a CD spectroscopy, when you see the characteristic bands, that tells you about the chirality being present over there. And that chirality is inducing some because of the amino acids over there, they are inducing chirality in the charge transfer bands. Similarly, in the second example, when we saw that how do we identify that at this particular pH, our system is working, if at all it is chiral. So using series spectroscopy, the job becomes very easy, where we can see at different pH. Series spectra is giving different distinctive peaks, and there we can identify the reason. Okay, because of the amino acids interaction with that particular H positive and involvement, it is increasing or diminishing the rate of H2 production. So up till now, is there any question? Otherwise, we can move further.
No question, ma'am.
No. So now there is another part, as we said, that topics that we have to cover. So we talked about the induced charge transfer bands, and we also see that how can we distinguish with respect to the pH, how we can say that it would be giving more H2 production or not. So these are certain examples. Similarly, if you understand the concepts of the amino acids and the chirality related to that and circular dichroism, then the job is halfway done. Now, the second is one of such examples of G quadruplex formation and topology. So don't get worried about the terminology. So I'll just briefly define. So this G quadruplex formation is just a nucleic acid arrangement. So similarly, the DNA we talked about, that is comprising of nucleic acid, proteins, and some structures. Also, there are guanine bases. These guanine bases is nothing but this one. This is a guanine basis. And these guanine bases, when, if you can see, there is one unit, this is second unit, this is third unit, this is 4 unit. That's why it is called as quadruplex, because we are having 4 units. And you can see they are interacting with each other because of this hydrogen bonding. I'll just highlight this. Okay. So here, I'm highlighting first unit by this. The second unit here. Third unit here. And fourth here. And you can see clearly that these are the hydrogen bondings that it is having. Because of the hydrogen bondings, these units are intact with each other and they get stabilized in presence of an alkali metal. So why are we discussing this? So as a simple definition, that these are actually a structural arrangements of nucleic acids such as DNA. So since we were taking a lot of examples from biology and where CD spectrum is helpful, so we are understanding that how DNA is having guanine bases and how their arrangement looks like. So their arrangement is looking like this particular way, where because of the hydrogen interaction, they get connected to each other. Now the main point over here is these guanine bases, they have a tendency to arrange in different patterns. So the guanine molecule is nothing but this one. So you can see the structure and we can name them. Already the numbering has been done. So this is having C double bond NH, that similar kind of peptide bond, and nitrogen moieties are there, free NH2 group is there. So we always start with closer to this particular C double bond, 1, 2, 3, 4, and 5. These are the numberings that we are giving, 1 to this one, 3, and this becomes 4 and 5 nearby this one. So when you will see over here, because of the different, when we have 4 units over there, so there would be different arrangements, like 3 would be above, 5 would be down, or 3 and 4 would be having same movement or something. So here, based on the topology that they are having, 4 units would be stacking with each other and will give you either the parallel shape or the anti-parallel one or the hybrid one. So in parallel, both the 3' and the 5', that the nitrogens we were representing, they would be facing similar direction. Like if this way and this way. In anti-parallel, they would be having an opposite like this way. So in anti-parallel also, there are 2 further topologies, chair form and the basket form. And when we talk about the hybrid is having a combination of both parallel and anti-parallel. If you will see over here, this is down and this is up. So this is a combination of anti-parallel, whereas this is down and this is down. So both are having a parallel combination. So that's why it is called as a hybrid. So these are the different possible topologies of a guanine basis, that quaternary arrangement over there. So how series spectroscopy? So we got to know that DNA is having guanine bases. We are just taking an example where we know that DNA comprises of the guanine bases and their arrangement is just like a quadruplex where 4 units would be there, and how the 4 are intact with each other because of the hydrogen bonding. And depending upon different topologies, they could be having different shapes over there, different arrangements over there. We have parallel one. If both 3' and F5' that nitrogens we named as, they are facing in the same direction. If they are facing opposite, that's anti-parallel. And if they have both combinations of, because we have four units over there, so there would be like combination of both parallel and anti-parallel existing together. So how series spectroscopy is helpful, and now you can see if this is a case of parallel, just as we saw in case of alpha helix, beta sheet, and random coil, there are different signatures in the series spectroscopy. Similarly, in parallel case, there would be one negative band at 240 and one positive band at 260. In case of the anti-parallel, there are one negative at 260, two positive at your 295 and 240, whereas hybrid is having both the signatures. So 295 taken from the anti-parallel at positive, 260 positive taken from the parallel one, and 240 negative taken from the parallel one. So this way we can see the structure. We can identify like what topology, what kind of structure it is having in DNA system. So this is very helpful in identifying such molecules which can't be characterized by using any other random technique. So that's where series spectroscopy becomes very useful. So is there any question? So then we can move ahead.
Ma'am, once again, explain, ma'am, anti-parallel, chair form and the basket form.
So you can just simply understand in this particular way. So I'm highlighting this 3 nitrogen and closer to this one. So when you have four systems over there, there would be different arrangements. One facing would be other, like this way. We are having hydrogen bonding. So which nitrogen is having hydrogen bonding with what nitrogen, we don't know. So depending upon that, they have been named as 3' and 5', as you can see, which are involved in the bonding over here. So this one becomes your 5' and this is your 3'. So that's why there would be a hydrogen bonding over there. And depending upon that, if both 3' and 5' are having similar direction. So here you can see the arrow is above and 3' arrow is also, sorry, this is down. If your 5' arrow is down, 3' arrow is also down, and here again it is down, right? So if both the thing or all the quaternary, whatever the groups are there, they are facing in the same direction, that will give you parallel geometry. Whereas if it is anti-parallel, that means one is facing down, one is facing above. This is the movement that we are having, that helical motion what we are having, but one is above, one is down, that is anti-parallel. And in hybrid, we will be having both the combination. As you can see in hybrid, this is down, this is down. So this becomes a combination of parallel. Whereas if you take this one and this one, this is down, this is above, that is an anti-parallel. So hybrid comprises of both parallel and anti-parallel, and anti-parallel will be having one above, one down. Is that clear now?
Clear, ma'am.
Okay. So as I was saying that how CD spectra is very helpful. So see this particular spectra. So there is red trace, blue trace, green trace, and pink trace. So just see this original one. So we are having here one in the negative and 2 in the positive, and we saw here itself 2 in the positive and 1 in negative, that is an anti-parallel. So just looking at the spectra, we can tell, okay, this is anti-parallel. Similarly, here it's 1 negative and 1 positive. That was the case of a parallel one. The third is again one negative and above positive, that's a parallel one. This is also one negative and one positive, parallel one. And here if you'll see one negative and two positive, that's a case of your hybrid. One negative and two positive, that's a case of your hybrid. So just looking at the spectra itself and the bands in what direction, positive, negative, and looking at the values, they would be lying near to that 240, 260, 295 region only. So they're not very difficult to remember. So you can predict which belongs to which topology. So this is the similar case as we saw in case of the alpha helix, beta sheet, and random coil. So there also in alpha helix, you saw that one would be above, two would be negative. Beta sheet, you saw one positive, one negative. The random coil, you saw it starts from the negative and it is having one negative, one positive. So is that clear now?
Clear, ma'am.
Okay, so this part is also done. Now the main part is coming, which is the various spectroscopies, and among that also our main topic is small spectral spectroscopy, which we will be talking about in next week, because the sessions or the week lectures will be starting from week 8. So today we will be taking up basics of the spectroscopy. Okay. So firstly, spectroscopy is nothing but a technique with which we know the two factors. Firstly, the intensity. Second is the energy factor. So normally, if you'll see the optical absorbance, or we were talking about the circular dichroism, it was giving us positive, negative, a certain range that was giving you an intensity of that certain point, whatever the measurement you're taking. And x-axis is normally a wavelength, and we know that energy is having a relation with wavelength, right? So generalizing, if we'll generalize it, intensity is actually dependent upon that concentration term, and energy becomes yours. Just a second. So this tells you about, like, it has a relation with wavelength, or we can say wave number, or we can talk about the frequency, right? So we know that E equals to hc nu hc by lambda or h nu, and this becomes c by lambda, or we have hc into nu bar. This is your 1 by wavelength, that is wave number. So 1 by wavelength is nothing but the wave number. So intensity is dependent on the concentration. It says that how much quantity of your thing has been absorbed or interacting, right? So this becomes a quantitative analysis. Whereas energy, like, in what energy is telling you about, like, a qualitative analysis. So this is a qualitative, like, about what is the quality of your spectroscopy you're actually measuring, like in which sample it is having this particular absorbance it is taking place, and intensity would be talking about like how many molecules have been absorbed and they are showing under the same time scale or same absorbance region. So that is a general way we define the spectroscopy and what kind of plot we are getting. So in